Hi, in this lecture video, I'll be discussing the synthesis of alcohol by reduction reactions. And there are three learning objectives of this lecture video. First is to recognize and understand the reduction reaction. And then second, to familiarize ourselves with the various reducing agents, then their reactivity and their selectivities. And third, understand the reaction mechanism of some of this reduction reaction. Once we understand one or maybe a few of the reaction mechanism, it will become very easy for us to figure out and understand the mechanism of all the reduction reaction. So now let's go back and discuss the first learning objective first. Recognize and understand reduction reaction. To briefly recall, reduction reactions are basically processes that add hydrogen to a molecule, in this case an organic molecule. So that's the meaning of reduction reaction in organic chemistry, a process that adds a hydrogen to a organic molecule. And in the course of this reaction right here, then the oxidation state of one of the atoms in the organic molecule would then be reduced. And of course that atom right there would then be the carbon. Here is an example of why we would consider this to be a reduction reaction. If we were to be looking at our ketone and how this ketone right here changes to a secondary alcohol in the course of this reaction right here, we will then see the following. The carbon-carbon double bond in this ketone right here is being broken. And now a hydrogen is then added to this carbon. So in this case right here, there is a hydrogen added right here. So this process right here adds a hydrogen to the carbon in this organic molecule, and therefore it is a reduction reaction. And of course, the oxidation state of this carbon right here will then be reduced, going from this reactant side into this product side. So this is an organic reduction reaction right here. And there are many carbonyl derivatives that can undergo reduction to produce the alcohol. Because the emphasis of this lecture video is on the alcohol, we'll be discussing the different carbonyl derivative that can be used to produce our alcohol. If we were to have a ketone, by taking the ketone and reacting it with the appropriate reducing agent, we'll be able to convert that into the secondary alcohol. Versus if we were to have a carboxylic acid, or its carboxylate, so that is the conjugate base form of the carboxylic acid, we can also take it and reduce that to produce our primary alcohol. And if we were to have an acid halide, we can also convert that, or by doing reduction, to convert that into the primary alcohol. The aldehyde can also be reduced as well, and the ester can be reduced as well to produce our corresponding alcohol. So these are some of the examples of carbonyl derivatives that would directly make the alcohol. And now let's go over the second objective. Recognize the various reducing reagents, their reactivity and their selectivity. So on the table down here, this is a list of the different reducing reagents that are out there. Now clearly this list right here does not cover every reducing agent, but this is the list of some of the most common ones, and how they are used for different purposes. So for an example, so here are the reducing agent, and in this case right here, we call this reducing agent right here the hydride donor, because they are donating electron through the hydrogen, and in this case the hydrogen is negative, so that's why we call this a hydride donor. And many of this reducing reagent right here would consist of a hydrogen with negative charge in them, and that's why these are reducing agent. So these are the different reducing agent right here, AlH4 all the way to H2. And as for what is in here, these are the structure of the substrate and the product when we take this different substrate and react this with the different reducing agent or this hydride donor. So for an example, we can see that the first one here listed here is LiAlH4, which is one of the reducing agent that we will discuss in more detail in a little bit. But if we were to now take this LiAlH4 and treat this with the acid halide, we'll be able to convert this substrate right here into the alcohol. And similarly, if we were to take our aldehyde substrate and react this with LiAlH4, it will be reduced to the alcohol. The ester can be reduced to the alcohol, the amide can be reduced to the amine, and the carboxylic acid or the carboxylate salt can be reduced into the alcohol. So you can see, by taking this LiAlH4 and treating this with this 4 different substrates right here, we will be able to produce our alcohol. And now, the table here lists many reducing reagents, and this is a very powerful tool right here, because it's important that we get the different types of selectivity. And so in the synthesis of an organic molecule may consist of different carbonyl functional groups in it. And sometimes it may be desirable for us to only reduce one carbonyl functional group, but not the other. So therefore, we want to be able to have a variety of reducing reagent with the different selectivity. So that way, we can selectively reduce one carbonyl functional group of our interest while not reducing the other one that we don't want. So therefore, all of this are very valuable tool, synthetically speaking. And so dibo is another example right here. It would have very similar reactivity to many of these functional groups compared to LiAlH4, except it do not reduce the iminium ion. And so a few ones that we will discuss would be this NaBH4, or called sodium borohydride. So sodium borohydride is very good in reducing the iminium. The dibo otherwise will not reduce, and it can also be used to reduce an aldehyde into an alcohol, while it does not reduce the acid halide into the alcohol, or the ester, or the amide, and the carboxylate salt. And so the reactivity of this different reducing agent right here come from this following principle: the reactivity of the hydride. So all of this reducing reagent right here consists of hydride in them, and depending on how reactive the hydride is, then that would dictate the chemical reactivity. And this is something that we will then find to be similar in all of this reducing agent. So a reducing agent, many of this reducing agent right here consists of the following. They consist of an atom, and a lot of time this atom right here happens to be a metal, and this metal is then bonded to a hydrogen. So this can be a metal, or sometimes boron, an atom with low electronegativity, because we know that metal and also boron as well have low electronegativity on them. And because this metal or have low electronegativity to them, when they are bonded to a hydrogen, we will then see that they be given an electron to this hydrogen right here. And now the hydrogen will be able to break off with the electron, and that's how we can produce our hydride. So we will then see that the less electronegative this atom or this metal would be, the more willing it would be in giving an electron to the hydride. So therefore we'll be able to produce more of this hydride right here. So therefore the different metals have different reactivity, and generally speaking, that's how it is. The reactivity of the reducing reagent directly correlate to the electronegativity of this metal or this atom that the hydrogen is bonded to. A lot of time, again, they are either metal or boron, because boron also have pretty low electronegativity. And the other factor that can also affect the reactivity of the reducing reagent is also the charge of this metal right here, whether this metal right here is positive or negative or neutral. They have different reactivity. As we can imagine, if this metal right here are negatively charged, now they do not want that electron right there when they're negative, right? Because they have very low electronegative. So a metal with a negative charge and having low electronegativity, this would make them the most powerful hydride producing agent that exists out there, right? Because when they're negative, they do not want to become negative, and now they have low electronegativity as well. So that means they do not want the electron. So therefore, they'll be very happy to give the electron to this hydride. So therefore, they can produce this hydride very easily. And we can see the electron density of this hydride right here would also pretty high as well. So that's why that they will produce the most powerful hydride reducing agent. And I hope that now you are able to get familiarized with the different reducing reagent and understand some of their reactivity and recognize their selectivity. And we'll be applying this different reducing reagent with the various substrate in a little bit. And hopefully by then you will have a more thorough understanding of this reduction reaction right here. And now, let's now go over to the third objective. So on this third objective right here, we will be focusing on some of the reaction of some of this reducing reagent and some of the substrate, and focusing on the synthesis of alcohol. So that is the main emphasis of this chapter. The first reducing agent that I will be discussing is the hydrogens. And in this case right here, catalytic hydrogen or catalytic hydrogenation reaction. This is very familiar to the hydrogenation reaction of the alkene and the alkyne that we have seen before already. In the case of the alkene, a carbon-carbon double bond, we can be taking a carbon-carbon double bond and treat this with the hydrogenation reagent in the presence of a metal catalyst, and we'll be able to reduce this bond right here to form the carbon-carbon single bond. And now the two hydrogen are added to this two carbon right here. So very similar mechanism is now seen in the reduction of a carbonyl derivative to produce the alcohol. If we were to take a carbonyl derivative, which basically consists of a carbon-oxygen double bond, and when we treat this with hydrogen in the presence of a metal catalyst, then now we'll be able to come in and reduce this carbonyl right here by adding a hydrogen to a carbon and a hydrogen to the oxygen as well. So in the course of this reaction right here, we'll be able to change this from a ketone into an alcohol. And the yield of this reaction right here is pretty high. So it's quite easy to do. But again, in order to perform this reaction right here, we need a strong and reactive metal catalyst. And hydrogens, in the presence of a metal catalyst, they're not just only reduce the ketone or the aldehyde, but it can also reduce the other substrate as well. At this table right here is listed. We can also reduce the imine, the acid halide, the aldehyde, the ester, and the amine. So in this case right here, these are the three substrates that can be reduced by hydrogen in the presence of a metal catalyst to produce the corresponding alcohol. And now, let's go over the second reducing agent, sodium borohydride, or NaBH4. That's the name for it. So this is a very common and useful reducing agent that provides very good selectivity. And its value it actually comes from its reactivity and therefore its selectivity. So this is only effective in reducing aldehyde and ketone at room temperature, but it will not be able to reduce ester and the carboxylic acid. And so therefore that way its value coming from with this selectivity. And whenever we use sodium borohydride, we normally use it in a polar probe solvents, alcohol and water. And this also provides the source of proton for our alkoxide as well. So because in the mechanism of the reaction, first the carbonyl derivative will then first be reduced into the alkoxide, and then follow once the alkoxide being produced already, because there's water in it. This can then come in and grab the proton from the water. So for this last proton transfer step. And here is the reaction of sodium borohydride. If we were to have a ketone or an aldehyde, so here if this is an R, then that will make a ketone, versus if this is an H, that will then be the aldehyde. So if we were to take our ketone or aldehyde and treat this with sodium borohydride in the presence of methanol or water, we'll be able to convert this into either a secondary or the primary alcohol. If we were to have a ketone, then the ketone will become the secondary alcohol, versus if we were to have an aldehyde, the aldehyde will then be reduced into the primary alcohol. And so basically, whether it is a primary or the secondary alcohol, it purely dependent on the structure of the starting substrate. And the mechanism of this reaction right here is as follows. When we look at the structure of sodium borohydride, it consists of the following. We have 4 hydrogen bonded to the boron. And in this case right here, that would then make this boron become negative. And this will then interact with sodium as the counter ion. So in this case right here, we can see that the boron is the atom that has low electronegativity. And in this case right here, if we were to be looking up the electronegativity of boron, its electronegativity is 2.0, and I have a negative charge on it. So it's not very stable with the electron. So therefore, it is very likely to then give an electron to the hydrogen, and therefore producing the hydride. So it is a source of hydride. But we can then see that this is not the most powerful reducing agent out there, right? Because of the electronegativity of boron. Boron, in comparison to the other metal, it would have pretty high electronegativity, right? Because if we were to be looking at, for an example, lithium or sodium, this metal right here have very, very low electronegativity. And those metal right here would then become more reactive compared to this boron. So in this case right here, boron is a reducing agent with a good but not a very high high reactivity. And that's the reason why it provides good selectivity towards only some of the substrate that can be reduced easily. And notice in this reaction mechanism right here, it happened as follows. So the sodium borohydride is the source of hydride right here. So it would then give electron to this hydride. This hydride take the hydrogen, take the electron, and come in and attacking this electrophilic carbon right here. So the reactivity of our substrate is then dependent on the reactivity of this carbonyl carbon right here. So in this case, because this have the positive charge on it, therefore the hydride come in and attacking this carbonyl carbon. And that once this attack has happened already, this carbonyl carbon now become exceeding octet. So therefore it has to break its pi bond, and now the electron is then donated to the oxygen and forming this alkoxide right here. And if we were to have alcohol or water in our reactions mixture, then now that provides the source of proton to protonate our alkoxide as well, producing this product over here. So in this case right here, since we start with the ketone, we will be able to make our secondary alcohol. And the hydride is then added to this carbonyl carbon. So different substrates have different reactivity dependent on the positive charge or the electrophilicity of this carbonyl carbon. So in this case right here, aldehyde can be reduced, and ketone can be reduced pretty easily, since the electropositive charge on this carbonyl carbon right here is pretty high. And now let's try some of this example right here using sodium borohydride. So example number 19. If we were to have this ketone right here, and we react this with sodium borohydride in the presence of methanol, then what would be the product? Then again, we would then see that this is the source of hydride right here. And now the hydride will be able to act as a nucleophile. So that the function of the hydride in all of this reaction, they are nucleophilic. So they will come in and attacking the electrophilic carbon, breaking this up, producing the alkoxide. And the alkoxide follow, then pick up the proton from the polar probe solvent. So in the end, this would then be the product of this reaction, our secondary alcohol. And now, note the following. This is something that's very important. Let's now talk about the stereoselectivity. So in the course of this reaction right here, we go from this molecule right here, which is achiral, to now producing an alcohol that is now chiral. Because this is a chiral center right here. And because this molecule is now chiral, it is important for us to specify its stereochemistry. And we can see that this reaction right here provides no selectivity at all in terms of stereochemistry, because this hydride can either be added in the front or in the back of this carbonyl. do not matter. So therefore, we'll be producing a racemic mixture of these two different products right here. And now let's try number 20. So in this case right here, we are taking an aldehyde with the alkene along with it as well. And we are treating this with sodium borohydride. So in this case right here, we know that this reagent will only react with aldehyde and ketone. So it can only reduce that, but not reducing our alkene. So our alkene will remain intact in the course of this reaction. So therefore, it will only come in and react with this aldehyde carbonyl carbon right here. So in this case right here, the product that we get in would then be as follows. After the protonation step, we then be producing our primary alcohol. And note that the hydrides from the reducing agent is now added right here. And therefore, this is now a primary alcohol. So whether it is a primary alcohol or a second alcohol that will be produced, it purely depends on the structure of the substrate again. If we start with the ketone, we can make our second alcohol. If we start with our aldehyde, we'll be able to make the primary alcohol. And now, let's try this third example right here. So in this case right here, we have this organic molecule that consists of an ester. So this is the ester right here. And this is the ketone. So we have two carbonyl derivative or two carbonyl functional group within one molecule. And when we take this and react this with this sodium borohydride, what would then be the product? Then we would then see that sodium borohydride is not strong enough to reduce the ester. So no chemical reaction will happen on this ester right here, but it will only come in to reduce this carbonyl ketone right here. So in the course of this reaction, we'll be getting this product right here. So the ester remains intact. And again, we'll be making a racemic mixture here in this case. Because there's no selectivity on this. So this reagent is not stereoselective. And now let's discuss why if there are the ketone carbonyl. In this case right here, this is more reactive compared to this carbonyl from this ester. So if we were to be looking at the electrophilicity of this carbonyl carbon right here, they have different reactivity. In this case right here, we can then see that all carbonyl carbon are electrophilic due to the partial positive charge on them. And between these two carbonyl carbon right here, which one would have a more partial positive charge on it? And the answer would then be this one. The partial positive charge on this one right here is by far much greater compared to the carbonyl from the ester. And the reason why that happened is as follows. If we were to be looking at this, so I'm going to drag this to make this a bit bigger. Okay, or I'll just make this become bigger. So the effect is that in this ester right here, this oxygen is donating electron to the carbonyl in the case of the ester. And because of this resonance effect right here, the carbonyl carbon in the ester are receiving the electron from this oxygen that reduces its partial positive charge. So therefore, it is not as reactive compared to the carbonyl carbon from the ketone that do not have any resonance effect to it. So that's the explanation why that this ketone right here is more reactive compared to the carbonyl from the ester, and thus can be reduced easily. So in this case right here, since this is a weak reducing agent, therefore it will not be able to reduce everything. It is not strong enough to reduce the ester, but only the aldehyde and the ketone carbonyl. And now let's discuss a very common and very powerful and in fact very universal reducing agent, lithium aluminum hydride, which is abbreviated with LAH, and the chemical formula is LiAlH4. So this is a very powerful reducing agent, and because it is very powerful, it is not selective, and it can be used to reduce pretty much anything. So in addition to the aldehyde, the ketone, the epoxide, the alkyl halide, and there are many other functional groups that can also be reduced by lithium aluminum hydride. So this can also be used to reduce carboxylic acid as well, ester, lactone, amine, pretty much all carbonyl functional group. Now, this is not strong enough to actually reduce the alkene, so that its selectivity right there. It can be used to reduce all carbonyl derivative, but not the alkene. And because this is very reactive right here, it can also react very violently with water. So therefore, a polar product cannot be present along with this reaction right here in the same reaction flask. But it still will produce our alkoxide. And now to protonate our alkoxide, we have to do the protonation step in a separate step right here after the reduction step. And one molecule or one equivalent of the lithium aluminum hydride is capable of reducing up to 4 carbonyl groups. And the reason why one molecule of it has up to 4 hydride in it. So that way that we don't need a one-to-one equivalent of it compared to the how many ever carbonyl that we have. And now let's discuss the reactivity of it. So in the case of lithium aluminum hydride, this is a chemical structure. So the lithium is bonded to the 4 hydrogen. And now there is a negative charge on this lithium, on the aluminum. And here will be the lithium right here as the counter ion. So we can see that aluminum is a metal and has pretty low electronegativity. So therefore, it is very much readily available to then give the electron to the hydrogen. And now this hydrogen would then be able to fall off as a hydride. And that's why this hydride right here, it's very powerful. And there's a lot of it. So if we were to have either our ketone, our aldehyde, our carboxylic acid, or our ester, we'll be able to reduce all of them into either a primary or a secondary alcohol. And please note that in this case right here, the OH and the OH group right here have fallen off of this carbonyl right here. So if we were to have a carboxylic acid and this OR group right here, they now get replaced by another hydrogen. So we would then see that for some of this functional group right here, the hydride are added twice to the carbonyl functional group. And that's how we can convert them into either the primary alcohol or the secondary alcohol. And this is the reaction mechanism right here. When we take our ester here and we react this with lithium aluminum hydride. So again, the hydrogen fall off and take an electron from the aluminum and then attack in this electrophilic carbon right here. So in this case right here, this is the ester. So the positive charge on this carbonyl carbon right here, even though it's not very high, but because of this hydrogen right here is very reactive, we'll be able to come in and attack this anyway to break this off. And now we are producing this intermediate. And once we have produced this intermediate already, and notice how that now the hydrogen, the first hydrogen, is then added or bonded to this carbonyl carbon. This is not a stable intermediate right here, so the electron is then donated down, and then this kick off this O methoxy group right here. So this will be falling off, and now we are producing our, so this substrate in this process right here, it now become an aldehyde. And if we were to have an aldehyde, we would not be able to stop right there, because this aldehyde right here, the carbon of this aldehyde would even be more reactive than the carbon from the ester. So therefore, another molecule of the lithium aluminum hydride would be able to come in and attack in this carbonyl carbon again, producing this into the alkoxide. And followed by the protonation step, that would then produce our primary alcohol. So an ester is then converted into a primary alcohol by undergoing the addition of the hydride twice. If we were to have an aldehyde or a ketone, then this would then undergo the reduction only once. So only one hydride would then be added to the aldehyde and the ketone functional group. Whereas up to 2 hydride molecules would then be added to the carboxylic acid and the ester functional group. And now let's try some of this example right here to make sure we know how to do this reaction. So in this case, we have this molecule right here that consists of both an alkene and a carbonyl in it. And when we treat this with lithium aluminum hydride on the first step, and again, this is done in ethyl ether, so that is the solvent that we are using to dissolve the lithium aluminum hydride. And notice now water, the protonation step, is done in a separate step. So the first step is with lithium aluminum hydride, followed by the protonation step, which is a separate step. So in this case right here, we then see that we have a ketone. The ketone would then be converted into the second alcohol. And that would then only get it one hydride added to the carbonyl carbon. So in the course of this reaction, this would then be the product. And we'll be making a racemic mixture of both of this stereochemistry, if this is a chiral center. And in this case, it is not, so therefore, it does not matter that we specify the word racemic. And now let's try this example number 24 right here. So in this case right here, we have the same substrate that we have seen on the previous example, and now we're treating this with lithium aluminum hydride. So we know that this now can reduce both the ester and the ketone. So this will be able to come in and react with both of this carbonyl carbon. It will then convert the first carbonyl, this ketone right here, into the second alcohol. And I'll be able to convert this ester into the primary alcohol, where 2 hydride would then be added to it from the reducing agent. So that would then be the structure of the product. Please try this 2 problem on your own.